You know, have you ever studied chemistry and felt like you're just memorizing a bunch of random facts? Well, this explainer is going to change that. We're going to build a map, a connected map of IGCSE chemistry to show you how everything, and I mean everything from the tiniest atom to a massive chemical reaction, all links together logically. Ready? Let's dive in.
Seriously, think about it. How can we possibly explain the entire material world? I mean, just look around you right now. The air, your phone, you. It's all just chemicals. It feels impossibly complicated, right? So where on earth do you even start?
Well, the answer is actually pretty simple and really elegant. Turns out, this whole complicated world operates on a surprisingly small set of fundamental rules. And if you can get your head around those rules, everything else starts to click into place. So that's exactly where we're going to start.
All right, Section 1, Chemistry's Core Principles, the building blocks. We have to start at the very, very beginning. Before we can talk about how stuff reacts, we need to know, what is this stuff anyway?
And it all comes down to the atom. Now you know the drill. Protons, neutrons, electrons, but listen closely, because this next part, it's probably the most important idea in all of chemistry. It's not about the whole atom, it's about the outermost electrons. That's it. Those little guys on the outside control everything. How an atom behaves, what it connects with, it's all down to them. They're the key to the whole puzzle.
So what's the deal with these electrons? Well, atoms just want to feel complete and stable. And for them, that means having a full outer shell of electrons. They've got two main ways to do it. First, there's ionic bonding. This is where one atom just straight up gives an electron to another. It's a total transfer. This creates a positive ion and a negative ion, and boom, they stick together like tiny magnets. The other way is covalent bonding. This is more like a partnership, where atoms share electrons. And that simple choice, to either transfer or share, that decision is responsible for basically everything, from the salt on your fries to the plastic in your phone.
Okay, so we've got bonding. Now let's talk about why it actually matters. This is where we connect the tiny, microscopic world of atoms to the big world we can see and touch. The kind of bond an atom makes decides the giant structure it builds. And that structure, it explains why things are the way they are. You know, why a diamond is super hard, and why a piece of metal bends.
So let's take a really common question. Why are metals malleable? Right? You can bend a paperclip, you can hammer a nail. Why doesn't it just shatter into a million pieces like glass would? The secret, as you probably guessed, is hiding in its atomic structure.
See, a metal isn't just a random jumble of atoms. It's actually these neat, orderly layers of positive ions. And all around them is this sea of electrons that just flow freely between them. So, when you hit the metal with a hammer, what happens? Those layers of ions can just slide past each other. The sea of electrons acts like a glue, holding the whole thing together so it changes shape instead of breaking apart. Pretty cool, huh?
But now, what happens if we make an alloy? An alloy is just a mix of metals. So now we're throwing atoms of a different size into that perfect, neat structure. Imagine you have a box of perfectly stacked marbles. Now throw a few big rocks in there. The layers are all messed up. They can't slide around anymore. They get stuck. And that's exactly why alloys like steel are so much harder than pure metals like iron. And you know what? This exact same idea explains a huge mystery. Why is diamond crazy hard, while something like methane is a gas? Well, in diamond, you've got a giant covalent structure. Every single carbon atom is locked to its neighbors with super strong covalent bonds. To melt a diamond, you have to break those bonds, and that takes a ridiculous amount of energy. Now look at methane. It's a simple molecule. To boil it, you're not breaking the strong bonds inside the molecule, you're just overcoming the weak forces between the molecules. It's like pulling apart sticky notes instead of breaking a steel chain. And here's a massive exam tip. Get this language right. Always talk about breaking strong covalent bonds versus overcoming weak intermolecular forces. It's absolutely critical.
Okay, so we know how stuff is built, but let's be real. In a lab or out in the world, things are usually all mixed up. So how do chemists actually figure out what's in a mixture and then separate it out? Well, that's where the chemist's toolkit comes in.
One of the first things you gotta learn is how to identify stuff. Let's do a quick fire round of the classic gas tests. You absolutely need to know these. For hydrogen, you use a lit splint and you get that classic squeaky pop. For oxygen, a glowing splint will relight. Classic. Carbon dioxide, bubble it through lime water and it'll go cloudy. And finally, chlorine. It'll bleach damp litmus paper, turning it white. And hey, let me give you a really important tip here. This is straight from the examiners. When When you're asked for a test, don't just write down squeaky pop test. That won't get you the marks. You have to describe the whole thing. First, what you do. Place a lit splint into the mouth of the test tube. And then, what you observe, a squeaky pop sound is heard. Give the full story, and you'll get the full marks, every time.
Now what if you need to separate something like ink? Your go-to method is chromatography. And the best way to think about it is like a race. You put a dot of ink on the starting line, the baseline. Then the solvent starts soaking up the paper. As it travels, it drags the different colored dyes in the ink along with it. But here's the clever part. The dyes that are more soluble, the ones that dissolve better, they travel faster and further. They win the race. And just like that, you've separated all the different colors from the original black ink.
All right, we've talked about what things are. Now we get to the really fun part, what things do. This is the action. This is about reactions, rates, and energy. This is all about the making and breaking of bonds.
So, every single chemical reaction has an energy change. It's a simple rule. If the reaction gives out heat, making everything around it feel warmer, we call that exothermic. Exo for exit, heat exits. Think of a bonfire. If it takes in heat, making its surroundings feel cold, we call that endothermic. Endo for enter, heat enters. You know, like one of those instant cold packs. That's a perfect example. But how fast do these reactions actually go? Well, the speed depends on how often the particles bang into each other with enough energy to actually do something. We call those successful collisions. And we can speed things up by making those collisions happen more often, by raising the temperature, or the concentration, or the surface area. Or we can cheat. We can use a catalyst. A catalyst is like a chemical matchmaker. It just provides an easier alternative path for the reaction to take, one that requires less energy to get started. So the reaction happens way faster, and the catalyst itself doesn't even get used up.
So we've gone on a pretty big journey, right? From single atoms all the way up to energy and reaction rates. But the real magic, the real power of chemistry, isn't learning about each of these things in isolation. It's seeing how they all connect, how they tell one single logical story. It's time for the big picture.
And here it is. This is the central idea of chemistry. It's a perfect chain reaction. It all starts with an element's atomic structure, specifically its electrons. That determines the kind of bonding it will form. The bonding, in turn, determines whether it builds a giant or a simple structure. And that structure is what gives the substance its final physical properties. See? It's a clear line from A to B to C to D. Everything can be traced all the way back down that path, right to the electrons.
So there you have it. That's the map. That's how everything in IGCSE chemistry connects. The big question now is, where are you going to go next on this map? Which one of these areas holds the key to your next big aha moment? Whether it's bonding or reactions or something else entirely, there's always more to discover. Thanks for joining me.